Hi everyone. So two lectures, one class ago, we talked about EDA, which is a useful way to go about investigating your data before performing any analysis. Now we're going to start to apply more concrete quantitative methods to our data in order to investigate relationships between variables. And in order to do that, we're going to start by reviewing some of the classifications of variables we talked about 2 lectures ago. And then we'll get into specifically when we have quantitative data as both the independent and dependent variables. If you don't remember what that is, don't worry, we're going to review that at the start of class. And specifically, the metric we're going to look at in depth is the correlation coefficient. Okay, so to review some of the classifications from variables that we learned 2 lectures ago, the first split in categorizing them is quantitative or qualitative. You can also think of this as numerical and categorical. The reason I put sometimes in parentheses is because qualitative variables or qualitative data can also refer to text responses that don't fall into categories. But this makes analysis very difficult, almost infeasible. So we're going to focus specifically on when you do have categories for those variables. The other split we talked about is independent versus dependent, and I'm going to give you 2 more sets of synonyms for that. So you can also think of it as explanatory to response or predictor to outcome. The way I like to think about it visually is on the x-axis is the variable that's explaining the variable on the y-axis. You might remember the point that in statistics, we're not informed as to which direction that relationship goes, but as a statistician, you might have an idea of what you're trying to predict and which variable you think will be useful in making that prediction. And so you will take the step of putting the predictor variable along the x-axis and the outcome variable along the y-axis. But again, the statistical analysis that we're going to learn about today does not give you any indication as to the direction of the relationship. It just tells you that the 2 variables are related. So again, as is common in statistics, we have some synonyms to refer to these. We talked about independent and dependent a lot 2 lectures ago. You should also know that the x variable can be referred to as explanatory or predictor, while the y variable, in addition to being known as the dependent variable, can be referred to as your outcome variable or your response variable. So we're going to explore a few different types of variable relationships, and in today's class we're really going to focus on when both the x and y, explanatory and response, are quantitative variables. Okay, so the first thing you want to be aware of, which we talked about last class, is before you do any kind of quantitative analysis, you can graphically investigate if a relationship exists and what that relationship might look like through a scatter plot. We'll go through a couple examples after this slide. But quantitatively, a more numeric approach to examine and objective approach to examining the relationship between the variables is the correlation coefficient and coefficient of determination. And those sound like 2 distinct concepts, but they're actually very closely related, and we're going to talk about the relationship between those concepts in future slides. So I drew this image that you're very familiar with about the difference between the sample and the population, and as you can probably guess from this image, in the sample the correlation coefficient is just called r, that's a little r, whereas in the population it's referred to as rho. That's the Greek letter, the lowercase Greek letter rho. And as with most statistics, when you're calculating them, 99% of the time you're going to be calculating them for the sample as opposed to in the population, because again, if you knew the population and you knew the truth, right, the analysis becomes a lot more straightforward. And then we're not going to get into linear regression in this class, But linear regression is a tool that kind of builds off of these correlation coefficients, and that is something we'll cover in more detail either in future classes or at the very end of class as optional material. But today's class is really going to focus on the correlation coefficient and coefficient of determination. All right, so before diving into these new quantitative approaches, let's start by going over some examples of scatter plots. So take a look at this scatter plot here. Tell me what you see. I want you to do two things. I want you to think critically about how this scatter plot might be able to be improved, and further, what message the person who made this plot is trying to convey. So starting with the first question, I think the biggest potential improvement on this scatter plot is the labels. So we're told the x-axis represents wine consumed, but we're not given any units. We don't know how much wine is being consumed over what time period. Similarly, for the y-axis, we're told it represents heart disease deaths. We're not told out of what size population or over what time period. So I think just adding those metrics in parentheses is very informative for people who want to think more critically about this plot. As far as the information it's trying to convey, this is something you may have heard on the news. It was a popular story for some time. That was obviously not being reported on by statisticians. And I say that because the news headlines would say things that were slightly sensationalist, like drinking wine may be good for your heart health. And a statistician would qualify that statement quite a bit more. So we can tell from looking at this plot that as the amount of wine consumed increases, the number of heart disease deaths decreases, right? However, and this is a point we made a couple lectures ago, we can't say that there's a causal relationship between wine consumed and heart disease deaths for a few reasons. One very important reason is there could be a lurking variable. And what I mean when I say lurking variable is another variable that's correlated both with wine consumption and heart disease deaths. And I'll give you one. So it could be the case. I'm sure you've heard there have been a lot of nutrition studies on the healthiest diet, and one of the healthier diets is the Mediterranean diet, which tends, and people who follow the Mediterranean diet are obviously people who live in that region, and people who live in that region tend to consume wine. It could be the case that the other components of their diet are what's decreasing the risk of heart disease death, as opposed to the wine in particular, right? And this is where things like randomization and blocking could be used to isolate the effect of wine. However, without knowing more details about the study or how this data was collected, we really don't know if there's a lurking variable present or not. That said, I do want to repeat the point that as a statistician, it's important to qualify any of your findings to avoid those kind of sensationalist headlines that might be misleading, and ensure that other people who read your findings are able to reproduce them in future studies. All right, so here's another example of a very famous data set known as the iris data set. So iris is a type of flower, and if you don't know what sepal length or sepal width is, neither did I, so I Googled it, and you can see in this image, it looks kind of like a leaf, but it's like the green part of the flower that's right below where the flower begins. So this is a data set you could get for free in R and many other statistical programs, just to do some analysis and test out various methods of statistical analysis. And we're plotting the length of the sepal versus its width, right? And looking at this, there appears to be a somewhat positive relationship, right? That's not necessarily the case. I could also see it being flat if I were to draw a line through it, which we'll talk about in more detail what that means in terms of correlation, or even negative, right? It's really unclear. There's not much of a relationship. I'd say, like, if you see a positive relationship, it's probably heavily influenced by these handful of points, and if you were to remove those, you might even see like a negative or flat relationship. So it's really hard to tell what's going on in this plot. But this is an example I wanted to show because visually, there's not much of a story here. However, if you add another variable through color, which is one way to include a third variable in your plot, you do start to see somewhat of a relationship. So these are different types of irises or flowers, and you can see that you can cluster this data based on the flower type. So like setosa flowers tend to live in this range of values of sepal width and sepal length. And even versicolor and virginica, which have similar values and a good bit of overlap, might be able to be classified somewhat. For example, on these extremes, they seem to be mostly virginica, and on this extreme, it seems to be mostly versicolor. So that's just one example that I wanted to show. It's not really clear to me if there is a relationship between sepal length and sepal width, but I think the plot becomes much more informative when we add a third variable, which is the species of iris flower. So that's just something I wanted to show. It's not super related to correlation, but I thought it was a good example. So moving on to correlation. Before we get into the mathematical definition of correlation, I want to review a little bit about variance, which you might remember is the square of standard deviation. So take a look at this slide. You've seen this formula before. I've copied it from past lectures. This is your sample standard deviation. Now remember, what's the relationship between standard deviation and variance? So hopefully you still remember that variance is just the square of standard deviation, and when you square something that's inside a square root, you just get rid of it. So s squared, also known as the sample variance, is this exact formula without the square root, and in fact I wrote it down over here. This is your variance. Now you'll notice I wrote xx as a subscript in the bottom. I know that mathematical notation is a little confusing, but there's a reason I did that, and that will become more apparent later. So this formula is your variance for your x variable. The formula immediately below it is the covariance of an x variable and a y variable, where both of those variables are quantitative. Take a minute to look at these two formulas and tell me what you notice. So what you should have noticed is that the formulas are actually very similar, and based on the subscript, you can replace, you can figure out, you really only need to memorize one formula here, because the subscript is kind of telling you what's going on. So in the case of covariance, you're taking your deviation, which we talked about as we were reviewing the quiz, of one variable, multiplied by your associated deviation of another variable, and summing up all those deviations and then dividing by n-1. And we talked about the intuition for that n-1 before. That's the formula for covariance, and it's very similar to the formula for variance. The main difference being that there is no other variable in the formula for variance. So instead of doing y minus y bar, it's like having a second x minus x bar, which is what's going on here, because with the square, you could also write that as x minus x bar times x minus x bar, right? That's what squaring is doing. It's taking that difference and multiplying it by itself again. So I know this was a lot of notation, probably a little confusing, but the reason I wanted to go over this is it's going to make understanding correlation much easier. So to review, this is the formula for variance, which I can write in this way, as the covariance between x and itself is the variance of x, whereas the formula for covariance between two different variables, x and y, is written in this way. So the formulas on this page all look very similar, and in fact they are very similar. The main split that I want to point out is that the sample correlation coefficient and the population correlation coefficient use slightly different mathematical notation because they represent slightly different things. So first of all, we use rho in the population and r in the sample. Similarly, here we're using the covariance, the sample covariance of x and y, whereas here we're using the population covariance of x and y. Hopefully you remember from a few lectures ago, the population standard deviation is written with a sigma, whereas the sample standard deviation is written with an s. So that's the main difference in these formulas. It's not huge, but it is meaningful, right? There's a big difference in interpretation between sigma and s. Now, row-wise, comparing these formulas, they are actually the same thing, but I wrote this in two different ways to kind of go over the intuition behind them. And I think the intuition becomes more clear when you understand that the idea behind a correlation coefficient is that it can be interpreted across any set of quantitative data. That means that the scale of the correlation coefficient should always be the same, right? Regardless of the data I'm working with, I should know what a correlation coefficient of 1 means. And that's kind of why we have this complicated term in the denominator. So let's go over the numerator first. This is the covariance, the sample covariance between x and y, which you saw on the previous slide. It looks a little intimidating, but it's nothing more than multiplying the deviation in x with the associated deviation in y, and then summing up all of those multiples. And then just like you do with an average, you divide by the count, but you have this extra -1 here, which we've talked about before. So again, very intimidating formula that's relatively simple if you stare at it and think at it long enough. So that's the numerator of our correlation coefficient. If we had left it like that, we would have some measure of the relationship between x and y, but it would be very hard to interpret across different variables. So the denominator of this formula is really just about standardization. It's about removing the units of x and the units of y from the correlation coefficient. And how do you do that? Well, remember what SXX represents. So if I go back to the previous slide, this is the variance of x. Or you could think of it as the covariance of x with itself, which is the same thing as the variance of x. When you take the square root of that, you get the standard deviation of x. Same thing with y. You get the standard deviation of y. So you could write this formula in this format. But I do think it's slightly easier to understand in this format because the idea, again, is to remove the units from the covariance that you calculated before. And you do that by kind of taking the individual variances of each variable or column, or however you want to think about it, and then taking the square root. And now you have a standardized statistic that is bound between 1 and -1. So whatever set of data I'm looking at, the interpretation will always be the same. So let's go through some examples of the correlation coefficient. And we're going to talk specifically about the sample correlation coefficient, also written as the letter R, because as I mentioned before, the vast majority of the time you don't have the population when you're doing statistics. So the first thing to know about the correlation coefficient is the sign tells you the direction. So here you have some scatter plots, and without doing any math whatsoever, you should already know the sign of the correlation coefficient. You can tell it just by looking at this data, right? As x increases, y increases, therefore the correlation coefficient is going to be positive. In this case, the inverse is true. As x increases, y decreases, right? They move in opposite directions. So there's a negative correlation. This no correlation scatter plot looks kind of like the iris data set in that, depending on what points you choose to focus in on, you might see something that's slightly positive or slightly negative, but it's really hard to tell what direction, if any, the relationship between the two variables is. So without doing any math, if I want to estimate R, the correlation coefficient, I know it's going to be positive in this scatter plot. I know it's going to be negative in this scatter plot, and I know it's going to be close to 0 in this scatter plot. The other thing to keep in mind is because we standardized it by dividing by the standard deviation of x and the standard deviation of y, it's bounded by 0 and 1. So that's what I wanted to get at in this next slide. The stronger the correlation, the closer your correlation coefficient is going to be to 1 in its magnitude or absolute value. So I think this picture demonstrates that really clearly. So here we have a perfect correlation. It lies exactly on a line. There's no variation on that line. So 1 indicates the strongest relationship. Similarly here, we have the same exact relationship, the same exact strength of the relationship, but it's moving in the opposite direction. So it's a negative 1. Right? Now here, this looks pretty close to a line, but there is some deviation around the line. So we have a correlation of 0.9, which again is still a very strong correlation, but 1 is reserved for when it lies perfectly on a line. Now 0.5 is, some say weak, some say moderate. Again, this is a little subjective here. 0 we talked about already is when there's no clear relationship. And I just wanted you to see that it goes in both directions, positive and negative. So just from looking at the scatter plot, you can kind of intuit what the correlation coefficient is going to be. You can intuit its sign based on the direction in which the data appears to be moving, and you can intuit the magnitude of that correlation coefficient, how close it is to 0 versus 1, based on the strength of that relationship. Okay, so this was a little bit about the intuition behind the correlation coefficient. I know we went over a lot of math into how it's derived. We will do some examples in the future. But I also want to talk about the coefficient of determination. Now, this might seem like a totally unrelated concept, and in fact, most times when this is taught, I think it appears to be totally unrelated. And if you Google this and try to look up the formula, it's going to seem like it's related to linear regression and it has nothing to do with the correlation coefficient. But the truth is that the coefficient of determination, also known as r squared, now this is a capital R as opposed to the little r we use for the coefficient of correlation, is actually equal to the coefficient for correlation squared. So you take your coefficient correlation, you square it, and you get your r squared. Now what does that tell you? Well, remember, our correlation coefficient is bounded between -1 and 1, right? So if I square it, the result is going to be bounded between 0 and 1, right? Because the negative numbers are going to become positive when they're squared. So this is another measure of the relationship between variables, but it's not as informative. Why do you think I'm telling you that it's not as informative? So the main detail you lose when using the coefficient of determination instead of the correlation coefficient is the direction, right? With the correlation coefficient, I know that a positive value indicates this kind of relationship in a scatter plot, whereas a negative value indicates this relationship. When I square it, I lose that information, but I get another measure of how closely associated those variables are. So a lot of times when the coefficient of determination is taught, it's taught in the context of linear regression. And I just want to be clear that they are closely related. In fact, if you just square your correlation coefficient, you will get your coefficient of determination, also known as R squared. In fact, you will hear many people refer to it as R squared instead of the coefficient of determination. We are going to cover regression a little later in this course, and at that time, I'll go into alternative ways to calculate this metric. But that's it for today. Thank you guys for your time, and we'll start covering some other types of relationships besides quantitative to quantitative data in our next lecture tomorrow.